Thank you very much, Marco. So today, coming back to maybe computational archaeology, one of the things that I've been doing on and off for the last 10-ish years has been to try to refresh a set of computational softwares that were based on very old paradigms. Uh, I'll try to explain why. Historically, these are methods based on potential flow theory, and they're applied mainly in naval and aeronautic engineers. In fact, these are the fields in which you have an external flow with fully attached flow past the streamlined bodies, such as ships and aircrafts. In these flows, most of the vorticity and viscous effects are confined to a very thin region. And sometimes you can altogether avoid representing it in your model. Sometimes you have to represent it in some way. So in naval engineering, problems like ship hydrodynamics, so the computation of resistance of a ship sailing in water, sea keeping, which is how the ship responds to waves, to incoming waves, propeller design, are problems that you can tackle with potential flow methods. And in aeronautic engineering, wing performance, aeroelasticity, which is fluid structure interaction with air, and propeller design again, because they both have propellers, a problem that you tackle with these models. Of course, potential flow is based on very, very impactful simplifying assumptions. So it's a very crude model. But given the very low computational cost, potential flow models were employed in the very first computer software tools for computational fluid dynamics. It's only natural that when the computational power increased, people started drawing their attention and developing more complex models, such as Navier-Stokes methods for the solution of Navier-Stokes equation. And so these methods have been left behind. However, they're still very much used in the early design stages because they're ready and fast in providing information. I've been using these methods for quite some time, and I noticed that the engineers use a version of these methods that are based on mathematical numerical models that are very old and that can be very much improved. So this talk will be about two problems, the wave-ship interaction for naval engineers and lifting surfaces, fluid dynamics, that I have been working on, on and off in the last 10 years, and benefited a lot from new mathematical methods to refresh the old softwares. What is the main trait of the problem that we are seeing over here? This is a nice Kelvin wake. Outside of here, we could have seen some, unless it was a bad day like this one. So this is the wake that is left by a ship that is advancing in calm water. And of course, this is all water that is being set in motion by the ship. And so this is lost energy because, of course, water has a weight. The main trait of this problem is that both air and water surround. So we have two fluids surrounding the hull, and that unless we accurately reproduce the behavior of the free surface, which is the surface, the sharp surface that divides water and air, we're not getting the resistance right. The physical model is pretty much represented over here. Of course, we want to evaluate the flow field, so the velocity and pressure field around in our case, only in the water volume that surrounds the hull. The ship is assumed to be a rigid body. Water is an incompressible fluid. The flow is irrotational, and the air in this model is represented only as a constant and uniform pressure with exerted on top of the free surface. Under these, very impactful assumptions, so incompressible fluid rotational field and simply connected domain, the flow field admits a scalar potential such that the gradient of the potential is going to be the velocity field, and The good news is that the mass conservation equation turns into our governed equation, which is the Laplace equation for the velocity potential. So we have reduced the amount of unknowns, because instead of a vector, we are looking for a scalar field. And the momentum equation becomes the Bernoulli's equation that you see over here. The better news, indeed, is that we have uncoupled the problem for the pressure and the problem for velocity. So we only solve for the velocity initially, and once we have the velocity as a post-processing step, we use the Bernoulli equation to get pressure. So how do we put together a boundary value problem with the Laplace equation? We need boundary conditions, and here you see that on the bottom and on the surface of the, so first of all, we solve, in a moving reference frame of the hull, so we are only, we are looking for the perturbation potential, the small caps phi that you see over there, which is basically the potential associated with the presence of the body, which has to fade at infinity, as you see on the gamma infinity boundary condition, on the truncation boundary of the computational domain. And then on we impose non-penetration boundary condition on the bottom surface and also on the hull, which can also move with a velocity that is a velocity of hull point. Let me see over there. Clearly, by a modeling perspective, the most interesting things happen on the free surface, and on the free surface, which is an unknown surface in our simulation, we have to impose two boundary conditions. One to understand whether the free surface is moved, and one to impose the boundary, potential on the free surface. Here. The two boundary conditions that we impose are a kinematic boundary condition that you see on top, in which the Lagrangian time derivative of the coordinate of a point, of a material point on the free surface, is equal to the Eulerian velocity of the fluid. And the second one is a dynamic boundary condition, which is obtained by a manipulation of the Bernoulli equation, so that we obtain the Lagrangian time derivative of the potential. So how do we solve this problem? Historically, the first one to propose a solution of this problem were Longuet-Hickey and Saint-Quaclet in '76 with a mixed Eulerian Lagrangian formulation. So you first take an Eulerian step, as you can see over here, with Dirichlet boundary conditions. So we start from a known potential on the free surface, 0 for instance at the start, and then we solve the Eulerian problem, so the fluid dynamic problem, the Laplace equation. So we have a solution everywhere, and in particular on the free surface. And then we use the velocity on the free surface that have been computed just to move by time advancing the kinematic free surface boundary condition, the free surface. After we do this, we also use we also time advance the potential using the Lagrangian boundary dynamic boundary condition, and we obtain the new potential to be imposed at the next time step, and we go and loop in this way. This is, of course, very good for environmental applications. It's still in use, for instance, when you want to understand how tsunamis evolve. The problem is that in the frame of reference of the boat, where you have an average stream, this runs into a bunch of problems. You can see already over here that after the first time step, my blanket, so the red part, has moved downstream, and after a bunch of time steps, it will abandon the region where I actually want to solve my equations. So this model is kind of unfit to carry out steady and unsteady flow simulations for ship hulls that move in the water. It is instead very good to understand how a wave moves in a closed basin. So clearly the problem is that we're using Lagrangian time derivatives, and mathematicians know that maybe using different kinds of time derivatives would be more beneficial, such as arbitrary Lagrangian area, but we'll get there in a second. Historically, this inability to treat time derivatives of quantities in a moving domain resulted in the fact that only steady solvers were used. Steady solvers were developed unpacking the Lagrangian time derivatives on the left-hand side, removing altogether the Eulerian time derivatives, which were difficult to compute in moving domains, and because in steady solvers they would be null, that was a good approximation. For instance, Oiterhaven, Karl-Erik Jansson had PhD theses that resulted in marine and in ship rapid and ship flow. There are two commercial software that are still today in use, and they're very accurate, but they can only do steady state simulation in this formulation. And so we tried to come up with a solution that allowed us to carry out both steady and unsteady simulation using the same formulation. This was not possible in that fashion. A good hint was the fact that at Michigan University, Robert Beck proposed a method which entailed time derivatives that were designed to have arbitrary horizontal velocity and a vertical velocity, which was to be computed, able to keep the markers, the free surface nodes, on the free surface. Okay, so this was basically a manipulation of the two previous equations to obtain a different time derivative. And in a PhD thesis of one of his students, this was not completely working, because the model was plagued by stability problems. And in fact, the only way in which it could properly work was to impose that the marker's velocity was v infinity, so that the markers would still drift away from the hull. And so clearly this model could not use for the purpose for which it was designed. That was putting together a model that could do steady and unsteady simulations altogether. The last thing that I would say is that in the very last year and a half, with some coworkers, we decided to avoid, we switched to a different kinematic free surface boundary condition. This is a non-penetration boundary condition for the free surface, which after all is like a flow surface for the water. And now the things look a lot like a fluid structure interaction problem, where the structure is the free surface, and you are basically imposing a non-penetration boundary condition on this surface, and then you have a dynamic equation, which basically is a balance of forces on the free surface, saying that the pressure must be constant on the other side. With this setup, I will show you in minutes, we were able to have a model that has that requirement, steady and unsteady simulations altogether. This is finally the boundary value problem that we are tackling. So we have the Laplace equation and all the boundary conditions that we have been discussing, including the semi-Lagrangian kinematic or ILE version, arbitrary Lagrangian Eulerian version of the kinematic and dynamic boundary conditions. So how do we solve these things? Historically is very, the boundary element method for this particular kind of problem is very much in use, because of course it's very easy to deform a domain just by deforming its boundaries. So you don't have to treat very much mesh deformations. Basically, this is what you call a boundary integral equation, and it is obtained by the Laplace equation when you multiply it by a green function, which is a function with this property that you see over here. The Laplacian of a green function is a Dirac centered in a point P. In our case, the green function is always the free space green function that you see on the bottom. What we do is basically we write a single boundary integral equation for every degree of freedom of the computational grid. Therefore, we are using a collocation boundary element method. This is how we discretize potential, the position of the point, and the potential normal derivative. This is an isoparametric formulation. And finally, it results into this matrix system, which has all full matrices except the diagonal matrix alpha. One noteworthy thing is that because the 1 over R formulation of the green function, basically we need to be able to carry out the quadrature of singular kernel integrals. And we do so by choosing appropriate quadrature or rules. Historically, this was not done, so sometimes this singularized method have the singularities in the collocation method move outside of the computational domain to avoid altogether the singularity. Of course, that drags in other problems, like where do I place the singularities, which in this case we don't have. So another problem in the formulation is that when we want to try and evaluate this on the free surface, just to compute where the free surface nodes have to move, we have the gradient of phi, which is discontinuous at the nodes and between different cells. Again, basically, this has been obtained through finite differences on the free surface. We have obtained it by writing the weak form of the equation that you see on the top and discretizing it with finite elements. So we obtain a sparse system that is very fast to solve with the dimension of the boundary element method system. And so we obtain this form, which is particularly convenient. So now we have a sparse block of the system, a dense block of the system, which was, and in the sparse block, we also have time derivatives. So because we are somehow lazy, we put everything into a vector, all our unknowns into a vector. We put everything into a big system of differential algebraic equations, and we tell to the Sandels, Ida Sandels library to solve it for us. If you want, this is like having a very big, fully coupled through structured interaction solver. In this image, I'm trying to show that everything is a fully coupled fashion with an implicit time advancing scheme. The other thing that I want to show is that for that red node, you also need to know where the ship is when it goes up and down. It needs to know that it has to go up and down. And so the code was also able to, I mean, we needed all these codes to talk also with the CAD file of the ship. So these codes are geometry aware, if you want. We used CAD files also for other purposes, such as mesh generation, but that's a story for another day. So we have these Newton iterations. The Jacobian is computed automatically, making use of the Saccado package library of Saccado package of the Trilinus library. And so we expect this thing to work because we have a nice time advancing scheme. Everything is supposed to work flawlessly. Instead, when we start this thing, nothing worked for at least 2 months in my life. I will never see a good solution because we were plagued by this sawtooth instability that was quite known in the literature. And when you take a look at this equation, when you think about it, because we went to the ALE formulation, as every time you go to an ALE formulation, arbitrarily Lagrangian Eulerian formulation, you obtain a new transport term. And in this case, this new transport term, especially when V infinity, so the velocity of advancing of the hull is very high, you can bump into instabilities due to dominant transport instabilities. Okay, so how do we borrow the solution from finite elements where this is solved through streamwise upwind Petrov-Galerkin stabilization, which basically entails the fact that in our small system where we evaluate, for instance, the phi over the t over here, delta phi over delta t over here, we are unbalancing the shape functions, including a correction that only acts in the direction of the fluid velocity. This is a recipe that worked. We have stable solution, as I'll show you in a second. The last thing is that we also do a posteriori error estimates for adaptive mesh refinements. And every time we do that, we stop and restart the simulation. We used a very simple Kelly error estimator because we don't have a better way to do a posterior to find an error estimator. This is an open problem, but as you can see, at least we have that when we run a simulation, the mesh is basically refined on top of the Kelvin wake featherlets, as you can see over there. This is what you see, and again, I sometimes take pleasure on the fact that when we look at this thing, it looks the same as the original image that you saw. This is a good feature of being a fluid dynamicist. I don't know if physicists can watch something. I mean, they can never watch the very small quantity that they're simulating. And yeah, that's a pleasure that I don't know if they will ever have. You know. They have many others, by the way, I guess. So the four horizontal lines that you see over there are vertical cuts in which on this peculiar hull, which is called DTMV 5415, is a benchmark hull for fluid dynamicists. They have taken measurements of the water elevation on those four vertical cuts. The one closest to the hull is the one on top, the one farthest is the one on the bottom, and the red line is the experiments, whereas the blue line is what we get from our simulation. As you can see, in some situations, they're very, very close. Probably the mesh is slightly under resolved far from the hull. This is pretty much the same plot. Basically, this is the height of the water in contact with the hull, plotted against the non-dimensionalized x coordinate. So at 0, we are on the bow. At 1, we are sitting on the stern of the hull, and this is the water elevation that you measured. Of course, it is non-dimensionalized. We have 3 experiments, and somehow these experiments have been done in different towing tanks, different facilities, and the blue asterisks that represent the result of simulation are pretty much in the middle of the experimental uncertainty. This is how we reproduce the total direct curve, which is eventually what the engineers want to have by this kind of simulations. The error is never higher than 2% on this overall curve. Now I could also start a video on this, but just to show, maybe I'll start it later if we have time. However, we have also run some simulations on this underwater spheroid, which allowed us to test the new kind of free surface kinematic condition. And we are successfully able to run unsteady simulation in which we pump waves into the domain. Also, when we don't pump waves, but we have the spheroid steadily advancing in calm water, as you can see, we can start with different ramps of velocity, but we always end up on the same solution, which is the solution with steady solution that we compute, and the steady solution is obtained with the same residual of the unsteady, just by imposing that velocities are null. So we have been successful in that regard. We also compared it to this previous solution made by Scullen on the same problem for the steady flow, and they look pretty much the same. So this is what happened in the last, I would say, 10 years in regard to the naval engineering problems. Recently, we've been asked by a company that is still working in nautical engineering. They're designing yachts, but you know now yachts have competition yachts. They have hydrofoils that lift them out of the water. So they want to study how wing behaves in 3D and in a very fast fashion. Now I'll give you a couple of historic, a bit of a historic perspective on how these flows behave. There's a theorem by Kutajukovsky that says that if you don't have vorticity, you don't have any kind of force exchanged by fluid and a structure. So we have a nice method that would work quite well as potential, and we are in this paradoxical situation, which is called, in fact, D'Alembert paradox, in which we can use this model, but we cannot obtain the forces that were, is exactly why we were using the model. And this was, of course, not in agreement with experimental observations. The reason that why that happens, I think it's shown quite brilliantly by this image. What happens on an airflow like this with a theoretical model in which the fluid has no viscosity and no mass somehow, is that the fluid is able to turn around this sharp corner, come back, and then restart without suffering. I mean, it doesn't suffer for these stiff accelerations, whereas instead in nature, air is heavy and goes completely straight over there. So we need to temper our model just to represent that, and we will obtain good forces even for this kind of flow. Just to make the story short, we need to add a surface that is called the wake surface, that basically is there to impose that the flow flows straight out of the trailing edge of the airfoil. For mathematical purposes, this surface is a surface of discontinuities of the potential. So this is how the boundary integral equation is modified. Somehow this is how we solve the new problem. The new unknown on the wake is the difference between the potential up and down. This becomes again a nonlinear problem because we have to impose that the pressure is equal on the top and bottom side of the wake. The most difficult thing here is to compute the velocity on the wake, and this is what we get. So this is the final form of the wake when we run our simulation. And again, we show a comparison with the experimental results for the wing that you have seen before. Again, this model works very well when discretization is carried out properly, and we're sitting pretty much on top of experimental data. This is the same kind of comparison, but on a rectangular wing. And so I come to my conclusions as I try to, and as I hope I have. I got through in my talk. Classical potential flow solvers are plagued by all sorts of problems: inability to compute time derivatives in the forming domains, evaluate singular kernel integrals, presence of instabilities due to dominant transport, and some recipes borrowed from numerical analysis have been fixing most of these problems. And so we had significant improvements, especially in the robustness and in the accuracy of the results. So there are many more things to do, but this is one of the things that I've been doing again on and off for the last 10 years, and this was a good occasion to show. By a computational perspective, these models, special boundary element method, as a full matrix, so benefiting from clusters just to have a lot of memory and to try is also a thing that was very beneficial. Okay, so I'll yield back to Marco, and thank you very much for the attention.